Hey guys, welcome. Yeah, so problem 6 of the 2018 BC FRQ. And to start, we're given the Maclaurin series for ln of 1 plus x. And that Maclaurin series is right here. Now, I have many videos on Maclaurin series, and one of those videos shows you how to go from this to this. So check out those videos. But yeah, more importantly, for this solution, notice that the Maclaurin series for ln of 1 plus x starts with n equals 1. So to get this first guy, you have to plug in n equals 1 into this general term. And so that means that to get the first term of the Maclaurin series for f here, we'll have to start with n equals 1. And equally importantly, to get the general term for this guy, let's just modify the general term for the Maclaurin series of ln of 1 plus x. And of course, once we have the general term for this function f, then we can get the first 4 non-zero terms very easily by plugging in n equals 1 through 4. So let's work on the general term. Now to start, the general term of ln of 1 plus x is that, right? So an, the nth term for ln of 1 plus x is given right here, right? So then first, let's look at this portion of f. Because all we have to do to get the general term for the Maclaurin series of ln of 1 plus x over 3 is to replace this x right here, which is replace that x right there, with an x over 3. So that would mean that we so far have an for f looking like the following. An for f will start to look like negative 1 to the n plus 1, and I'm looking over here. And like we said, we're just going to replace that with an x over 3. So I have that, and then I have x over 3 to the n, and then I'll have that divided by n. Okay, cool. First, notice that I can simplify this to read as follows, which is negative 1 to the n plus 1, and then x to the n, and then, x to the n, and then divided by, and it'll be n times 3 to the n, right? Okay, cool. Now, this will be the general term in the Maclaurin series for ln of 1 plus x over 3. So if we want f, right, all we have to do is multiply by x, that x right there. So we just have to multiply by x right here. I can multiply in front, but I'll write it right there. And so we have to multiply by x right there. Now, this an, which is right here with that red x, is the nth term in the Maclaurin series expansion for this function f. Yeah? Okay, cool. So let's get rid of this middle guy right here and scoot this to the left and simplify it a little. So we see that for f, the nth term in the Maclaurin series expansion will be what I'm about to write in red, which is an will equal negative 1 to the n plus 1. And then these guys will combine to x to the n plus 1. So x to the n plus 1, and then divided by n times 3 to the n, right? So divided by n times 3 to the n, right? Okay, cool. All right, so now that we've got the general term, like I said, it's pretty easy to get the first 4 non-zero terms. We just plug in n equals 1 through 4. So when n equals 1, we have a1, the first term, will be negative 1 to 1 plus 1, so negative 1 to the second, which is positive 1, and then x to the second, and then 1 times 3 to the first, so that's just 3. So this is just x squared over 3. X squared over 3. All right, and then a2 will be n equals 2, so that's negative 1 to the third, and so that's negative 1, and then x to the third, so that's negative x cubed, and then 2 times 3 squared. So negative x cubed divided by 2 times 3 squared. And yes, we can write this as 18, but we're not going to. And then a3 will have to be negative 1 to the fourth, that's positive 1, and then x to the fourth, so x to the fourth divided by, and then it will be x to the fourth divided by, n is 3 this time, so 3 times 3 to the fourth, and 3 times 3 cubed, sorry, getting ahead of myself, because I wanted to combine those into 3 to the 4th. But n is 3, so that'll have to be 3 to start, right? Okay, but you can't combine these guys into 3 to the 4th. Feel free to leave it like I have, or just write a 3 to the 4th there. Either should be fine for the AP exam graders. And then A4, the 4th non-zero term will be -1 to the 5th. So that's -1, and then x to the 5th. And so we'll have -x to the 5th, and then divided by, and then it will be 4 times 3 to the 4th. And not much simplifying we can do here, right? Okay, cool. Now, because we'll need this 4th term for something we have to do later in part C, I'll set it aside here, but we're done with part A, so I'm just gonna delete these guys. Yeah, okay, cool. Maybe I shouldn't, because we also need AN. So let me keep AN, right? Okay, all right. So A sub n is right there. And again, this A sub n is for F, in case you're like dozing off. Okay, all right, so let's go to part B. Part B has this. So it says, determine the interval of convergence of the Maclaurin series. Shoot, I have to have part A like showing in order for us to, okay, there it is. So it says, determine the interval of convergence for the Maclaurin series of F. Show the work that, yeah, okay. So we know that the interval of convergence is found by taking the limit as n goes to infinity, and then of the absolute value of an plus 1, the next term, divided by the previous term in the Maclaurin series expansion for F, and setting this to be less than 1, setting the limit of the absolute value of that quotient in there to be less than 1. That's how we're going to find the interval of convergence. So doing exactly this for this an will have us write limit as n goes to infinity of the absolute value of and it'll be -1 to the n plus 2, and n plus 2 because we're looking at n plus 1 there, so we have to replace that with an n plus 1, so we'll have n plus 1 plus 1, yeah, and then so x to the n plus 2 for similar reasoning, and this divided by, and then it's n plus 1 in place of this n, and then 3 to the n plus 1. And everything I wrote right here, that's just simply a sub n plus 1, right? It's simply a sub n plus 1 right here. So we need to divide this by a sub n, which is right here. But it's the same as multiplying by the reciprocal, so I'd rather do that. Multiply by the reciprocal of this guy. And so that will mean we multiply by n times 3 to the n, and then divided by, and then it will be -1 to the n plus 1, right? And then times x to the n plus 1, right? Okay, cool. And then we close off the absolute value and say less than 1. And hopefully a lot of stuff simplifies, and it does, right? So for example, this 3 to the n, let me do it in a different color. This 3 to the n right there, and that 3 to the n plus 1 turn into a 3 in the denominator, otherwise everything else disappears. And then this guy and this guy cancel to a -1 upstairs. But because of the absolute values, I don't even have to worry about that -1 right there. And then this guy and this guy will have to cancel into an x, and so we just have that left in the numerator and that left in the denominator, along with that 3 in the denominator. Okay, so this is simplified tremendously. And so what we have now is limit as n goes to infinity of the absolute value of what's in the numerator, n and x. So we have n times x. And then in the denominator, we just have an n plus 1 times a 3. So n plus 1 times 3. Right, and then now when n goes to infinity, clearly the quotient, and let me do it in a different color, the quotient n divided by n plus 1 goes to 1 as n goes to infinity, right? So first, let me write my less than 1 here. We need this to be less than 1. But once we send the limit as n goes to infinity, what we have will reduce to just the absolute value of x over 3, and that's because, as I said, when n goes to infinity, the quotient of n and n plus 1 goes to 1. And so we just have this is less than 1. Yeah? Okay, cool. My writing getting sloppier by the minute. Okay, anyway, now let's get rid of all of this and finish solving, right? Okay, so to finish solving, we just have to solve this absolute value inequality. And I assume you know how to solve absolute value inequalities because, yeah, you should have learned that in like algebra or something. Anyway, from here, you should know that what you have to write is -3 is less than x is less than 3. Done, right? Not quite, because we have to now test the endpoints because we don't know what happens when x equals -3 or when x equals 3. So to test the endpoints, what we have to do is replace this x with a -3 first and then with a 3 and see what happens. You can do it in reverse order, but I'm going to start with the -3. So an when x is equal to -3 is going to turn into -1 to the -1 to the n plus 1, and then I'm replacing this x with a -3, right? So that'll be -3 to the n plus 1. But notice I can write -3 to the n plus 1 as -1 to the n plus 1, and then times 3 to the n plus 1, right? And I want to do that. You'll see why. And then, of course, in the denominator, there's no x, so I just still have n and then 3 to the n. Yeah? Okay, cool. Now, look at what's happened here. We've got -1 to the n plus 1 times -1 to the n plus 1, which is -1 to the n plus 1 squared. And therefore, for any n, it will be a positive quantity, right? It will be +1, regardless of the n. So I could just get rid of what I just circled in blue. And so what we have reduces to simply this, which is 3 to the n plus 1 divided by n times 3 to the n. And by the exponent rules, then we see that we can get rid of it. What just happened? Okay, I wrote in white. Okay, anyway, this and this cancel into a 3 in the numerator. And so what we have for the nth term when x is equal to -3 just reduces to 3 times 1 over n. And as an infinite series, we know that 1 over n is the harmonic series and it diverges. And so 3 times the harmonic series will also diverge. So for that reason, this strictly less than is appropriate. In other words, at x equals -3, the series for f of x diverges. Okay? All right. So we do kind of a similar thing, but this time for x equals 3, and then we'll be done with part B. So when x is equal to 3, we'll have -1 to the n plus 1, and then 3 to the n plus 1, and then divided by n times 3 to the n, right? Now we can write this as -1 to the n, and then times 3 times 3 to the n, and then divided by n times 3 to the n, right? Okay, and then look at what happens. We can do this, and then we can combine this guy and this guy into a -3, and so we'll have -3 times -1 to the n divided by n. But as a series, this guy right here, sorry, circle too much. The guy in the square brackets, this guy right here, is the alternating harmonic series, which we know converges. So -3 times the alternating harmonic series also converges. So that means that we'll have to include this endpoint. And so that's that for part B, and let's move on to part C, and we'll be done, finalement. Okay, so part C. Can get rid of part A too. Part C says this. All right, so we're using the alternating series error bound to find a bound for the approximation given by P4, the 4th degree Taylor polynomial for F. Maclaurin series, sorry, which is a Taylor polynomial centered at 0. So this is why I saved this. because we know from experience or from knowing the alternating series error bound that this guy will be bounded by the first unused term, right? The first unused term is this guy right here. So let me write it down, and then we could move on. Well, actually, I'll remember it. So negative x to the fifth over 4 times 3 to the fourth, right? So we know that what I'm saying is we know that p 4 of 2 minus f of 2 will be less than the norm of the first unused term evaluated at 2. So that's the absolute value of negative 1 to the n plus 1, and it would have been x to the fifth, so 2 to the fifth, because x is 2, and then divided by, and then this divided by, and our denominator was 4 times 3 to the fourth, right? Okay, cool. And obviously this negative 1 to the n plus 1 we can get rid of because of the absolute values, and so we'll have that this equals 2 to the fifth is 2 squared times 2 cubed, and then we have divided by, and no need for the absolute values anymore because as soon as I get rid of this, everything else is positive. And then this 4 here is 2 squared, which is why I wanted to write as 2 squared in the numerator. And then we have 3 to the fourth, and so canceling these guys, we have that this guy is bounded by this number, which is 8 over 81. Yeah? Okay, cool. 8 over 81, or you could just write 2 cubed divided by 3 to the fourth. I'm sure you'll still get full marks. All right, cool. I hope you enjoyed this, and I hope it was helpful. Take care.